All right, thanks. I'm very happy to be here and have the honor to speak here in the beautiful city of Ghent with such a fantastic research group on tensor networks to present to you a work, the minimal canonical form of a tensor network, which is a joint work with Arturo Acuaviva, Visu Makam, Harold Nieuwboer, David Pérez-García, Friedrich Sittner, and Michael Walter. I'm Freek. And we're from the universities of Amsterdam, Bochum, Copenhagen, and Madrid. So I'll start with like a little bit of motivation. I'm sure many people here know tensor networks, but nevertheless, I'm going to begin saying a little bit about what is a tensor network, what it's good for. So in quantum physics, in many body physics, we have complicated big quantum states. They have an exponential number of amplitudes. But really, one can sort of, there is a notion of locality, and the idea of tensor networks is to somehow encode the physics into local tensors and combine this into a big global state. And this has been a very powerful idea over the last 20 or so years. It has been useful to classify topological phases. It has been very useful for very accurate numerics. And also, it's actually quite interesting for simulating or improving quantum computing. And in this talk, I'll tell you something about a project we did to actually just improve a basic linear algebra method for tensor networks. So what's a tensor network? Well, if we're given a tensor, so here I have an example with 3 indices, then we write this graphically as a blob with 3 legs. Each of the legs correspond to one of the indices. And if I have multiple tensors, then I can connect edges, and that just means that I contract the indices. So I sum over this joint index like this. All right, so even if you've never seen it, an example you certainly know is that of matrices. A matrix is just a tensor with 2 legs, and if I connect one of these 2 legs, that just means that I multiply the matrices. And then if I also connect the other 2 legs, then I compute the trace, the product of the matrices. So it's a very simple example. A second example, also many people will know, is a matrix product state. So here I take a 3 tensor, and it has 2 legs with dimension capital D, which is the bond dimension, and 1 leg with dimension little d, the physical dimension. That could be a qubit, and the bond dimension typically is something that you may vary. And then what you do is you contract all the bonds, like the virtual bonds with the bond dimension capital D, and you get a resulting state which still has, let's say, n legs, and you should think of that as representing, for instance, the ground state of some spin chain. And this is a very useful object. And in this talk, what we'll do is we will take the same tensor at each side, so it's like a translation invariant spin chain. All right, so why is it called matrix product states? Well, I mean, this is not very important, but we can also think of each of these tensors as a tuple of matrices, and then if we compute the amplitudes of the state, it's really a product of matrices that we compute the trace of. All right, so another important example is the generalization of this to higher dimensions. So in 2 dimensions, for instance, we may take a tensor with 5 legs, 4 of which have this bond dimension, and 1 is the physical dimension. And then we can contract on a 2-dimensional lattice, let's say with periodic boundary conditions, and we get a state on a periodic lattice. So this is known as PEPS. And this is good for instance, describing ground states of 2-dimensional lattice Hamiltonians. All right, so we've seen what is a tensor network. Now I want to tell you a little bit about what's a canonical form. And again, I'm going to start with sort of the baby example of a matrix. So if I'm given 2 matrices, A and B, then I can look at all the tensor contractions that I can make with them, and sort of the only thing I can do is just take a bunch of copies in a row and contract them cyclically. And I can ask, when do I get the same result for all system sizes? And the answer is that this happens if and only if they have precisely the same eigenvalues, because these things are just traces of the matrix to the power n. Okay, so that was a simple observation. And it's closely related, another simple observation, to a group action on my matrices. So if I have 2 matrices, then if I have my matrix, I can apply an invertible matrix to it and conjugate by that matrix. And we see that if we compute the tensor network contraction, the G and G inverse, the invertible matrix, they just cancel against each other, and this leaves the trace invariant. Okay, and just sort of an observation is that these tensor network contractions here, which are just the traces, they are really all the invariant polynomials of this group action. So this is just an observation. So now let's go to the tensors that we're really interested in, these MPS and PEPS tensors, and there we also have a natural group action where we act with, by conjugation on the bond dimensions with invertible matrices. And if we have MPS, then there's a single invertible matrix. If we have PEPS, then we have sort of two directions in which we can apply a different invertible matrix. And again, just like in the matrix case, these so-called gauge symmetries, they preserve the many-body state. So if I apply these matrices, then and I compute tensor network contractions, then G and G inverse cancel. I get the same many-body state on any system size, both for MPS and PEPS. So what we see is that there's really a redundancy in the description of the tensor if we're interested in the many-body state, and we are interested in the many-body state. So the question is sort of how to get rid of this redundancy in the description of the tensor. And the answer is to pick a good canonical form. So very loosely, you can think a little bit of this as that for matrices, you can sort of choose which basis you want to look at the matrix, and often it's nice to look at the basis in which the matrix is diagonal, and that's very helpful, as you will all know from experience. And similarly, if we have these tensors, there is this freedom of choice which tensor we look at, and we try to pick a nice one, and that's good for our applications. So in MPS, this is a very well-known thing, and if we have a tensor M, then we say it's in left canonical form. If, well, we take this tensor, and we take another copy of it, it's a complex conjugate actually, and we contract the physical dimension and one of the bond dimensions. And then we demand that the result is proportional to the identity. Or if you want, you can also think of this, that I think of my tensor M actually as a quantum state, and I compute the reduced density matrix on one of the virtual legs. And this has to be proportional to the maximally mixed state. And now a very well-known fact from tensor network theory is that for any tensor, there exists some invertible matrix that brings my tensor into canonical form. And there's some fine print here. There is actually a little subtlety in the procedure, like sometimes you have to somehow put some off-diagonal blocks to zero. A little bit similar as for matrices, that we have the Jordan normal form, but it still has some off-diagonal blocks. And in this case, we sort of want to put them to zero. Okay. And so what are its properties? Well, this canonical form is unique up to the action by unitaries. I mean, that clearly does not destroy the condition, so that's a freedom you have, but it's also the unique freedom that you have. And just like diagonalization of matrices, this is a very powerful tool in MPS. A key result is the fundamental theorem of MPS, which more or less says that if I have two tensors M and N, then they give rise to the same many-body state for all system sizes, if and only if they have the same canonical forms. So this has many applications. For instance, this is crucial if you want to do the classification of symmetry-protected phases for MPS. So it's a very important theoretical application, but it's also something that's used in numerics all the time, and it improves numerical stability. It's used to truncate bond dimensions and other things. So let's now have a look at a comparison between MPS and PEPS. So for MPS, some things are very nice in the sense that I can contract MPS efficiently, whereas for PEPS, the contraction is actually hard. So it's MP hard or even sharply hard, even if I keep the bond dimension low. And secondly, if I look at the question, do two tensors give rise to the same many-body states for all system sizes, then for MPS this can be decided in polynomial time, for instance by computing this canonical form, whereas for PEPS this problem is actually undecidable. It's been shown by Scarpa et al. And that kind of suggests that there can be no fundamental theorem for PEPS in general, as we saw it on the previous slide, because that would directly give a way to decide whether two tensors give the same state on all system sizes. It does exist for restricted classes of tensors, for instance normal tensors, But in principle, there seems to be a barrier here for general tensors, or maybe there can be a good canonical form. Let's see. We make a proposal for a minimal canonical form for PEPS. We call it the minimal canonical form, and the reason is that it's initially formulated as an optimization problem. So what we do is we take the tensor, we look at this group action that I defined, and then I look at the let's see if this relation point works. Yeah. So I look at the orbits under this group action on my tensor. I take the closure of that set, and we minimize the 2 norm in this set. So if S is in this orbit, then this object here computes the 2 norm, and we optimize over this. We compute the minimum norm. All right. And this I define it here in 2D, but you can do it in any spatial dimension. And there have been previous proposals for canonical forms for PEPS, but those were more heuristic and intended for numerics. And this one is sort of nice in the sense that it's the first rigorous definition that has nice provable properties. So let's have a look at those provable properties. I start with a definition. So I say that 2 tensors S and T are gauge equivalent if I take their orbits under this group action and I take the closure, and this is non-empty. So taking the closure still means that they have the same many-body states because of continuity. So this is a notion that we call gauge equivalence. And then our first main result is that, well, this minimal canonical form I defined in the previous slide, it exists, and it is unique up to action by unitary. So that's just as we saw for the MPS canonical form. And moreover, 2 tensors have the same minimal canonical forms if and only if they are gauge equivalents. Okay, so this really justifies the terminology canonical form, that it completely fixes this gauge symmetry up to unitary symmetry. And moreover, a second result is that, well, we defined the problem as an optimization problem. It's maybe not so nice. And we actually also have this nice diagrammatic criterion. So a tensor is in minimal canonical form if and only if it satisfies this symmetric condition, where if I think of the tensor again as a state and I compute the reduced density matrix, then sort of the left reduced density matrix and the right reduced density matrix are equal up to a complex conjugation, and similarly in the other direction. So it's sort of a symmetric condition. And the tool to prove these results and the way we actually came up with these canonical forms is something known as geometric invariant theory. So geometric invariant theory is a very natural tool in this context because it's a study of group orbits using algebraic geometry. So I'll give, again, a baby example using matrices. There I have the group action of invertible matrices on d by d matrices by conjugation. And if we look at its orbits, well, then we see that we can transform to any, if we have a matrix M, we can transform to any matrix with the same Jordan normal form as M. And we can take the closure, and it can contain strictly more already in this case. So for instance, if we have a Jordan block with a 1 in the corner, then by this sort of simple trick here, we can actually set this Jordan block, that this 1 in the Jordan block, to 0 as we go to the closure. So the closure is strictly bigger. And the proof of our results is a direct consequence of something known as the Kempf-Nest theorem in geometric invariant theory, which is precisely about the study of minimum norm vectors in group orbits. And sort of our existence results a direct reformulation of this Kempf-Nest theorem, and the conditions on the minimal canonical form, they follow from setting the gradient of the norm to 0, more or less, and then the Kempf-Nest theorem guarantees that this is the sort of unique solution to that. All right, so just a little observation is that actually you can also do this for MPS. It works in any spatial dimension. It gives a new canonical form already for MPS, and there, of course, the theory was already completely understood. There was a completely fine canonical form already, but what is kind of nice is that this geometric invariant theory gives a very clean framework, and for instance, this fine print of setting off-diagonal blocks to 0, that's sort of taken care of automatically by going to the closure in the group orbit. All right, we also prove a version of a fundamental theorem for PEPS, and it has to be, it's a different fundamental theorem. So what we say is that we have that two tensors S and T, they are gauge equivalent if and only if they give rise to the same tensor network on any contraction graph. So I widen the class of contractions. I'm not only allowed to put them on a periodic lattice, but also I'm just allowed to make any contraction where I connect left and right and sort of up and down. And if I look at all those graphs, then I get equality on all possible contraction graphs if and only if the tensors are gauge equivalent, so if and only if they have the same minimal canonical form. So now the problem has become decidable, and just a few words about the proof. Again, the proof is sort of straightforward from geometric invariant theory. The tensors T and S have intersecting G orbits, so they're gauge equivalent, if and only if they're equal on all invariant polynomials with respect to the group action. So that's a fact from geometric invariant theory. And we argue that these polynomials are in fact generated by these tensor network coefficients from arbitrary contraction graphs. All right, so just a quick question. So we have to check a priori all possible contraction graphs, but we show that it actually suffices to check equality for a finite number, for finite sized graphs. And once we know that, it's actually true for all sized graphs. And for PEPS, the number of vertices that you have to check on is actually exponential in the bond dimension. It's both necessary and sufficient, we show. While for MPS, it was already known from previous work that this is the number of vertices you have to check is polynomial. In fact, it's quite small. So again, here we see this difference in complexity between MPS and PEPS. All right, so a final question that we address in our work is, so given a tensor, we want to, of course, compute the minimal canonical form. I mean, that would be important in numerics. And how do you actually compute it? Because we formulate it as this optimization problem. And fortunately, so it is certainly a non-trivial question. And fortunately, there has been a lot of progress recently on optimization over non-commutative groups, and precisely in this context of geometric invariant theory. So we leverage these algorithms, and we show that one can approximate the minimal canonical form up to error epsilon by using either of two algorithms. So the first algorithm is geodesic gradient descent, and it uses the fact that this group action satisfies that under this group action we have not so much convexity, but we have sort of convexity along geodesics in the relevant space, and this gives rise to a nice algorithm. And then there's also another algorithm which also uses second derivative. It's like a Newton's method in this same non-commutative setting. And so these give algorithms which run respectively polynomial 1 over epsilon and polynomial in log 1 over epsilon. And the dependence on the bond dimension is not so good, what's provable. But for this first method, actually, if we look at a different error measure, which is more how accurately this condition is in the minimal canonical form is satisfied, then we actually do have a polynomial dependence in D. And also this gradient descent, it's easy to implement and it works very well in practice. So that's nice. All right, so the conclusion is that geometric invariant theory is a really natural framework for studying tensor networks and these gauge symmetries, and that we show that importing results from geometric invariant theory leads to a nice new canonical form. We hope that there's interesting future work to be done. So first of all, we were not really experts in numerics, and I think it's very interesting to see whether it's actually useful for numerics. Secondly, what's very nice is that this geometric invariant theory is very flexible, and you can directly apply it to any other setting where you just have a different symmetry group, and the same machinery gives you directly the same results. And it's also, I think, interesting to look further at the case where we do not have the same tensor at each side, but different tensors at each side. Thirdly, I think it's interesting to think a bit more about what's the relation to topological order. So we saw that we looked at these contractions on arbitrary graphs, and that's a little bit like putting the tensor network on some non-trivial manifold, and maybe there is something more interesting that can be said there. And finally, there is a bunch of open questions about the algorithms for computing T-min. So I want to sort of briefly make an advertisement that the University of Copenhagen is looking for a professor. And with that, after this advertisement, I would like to thank you a lot for your attention. And please talk to Michael, Harold, or me if you have any questions.
Okay, thanks a lot for this great talk. Other questions?
Yeah, thanks for the very nice talk. That's an obvious question. Like, have you thought about generalizations to other? Oh, sorry. Here.
Oh, sorry, I didn't see.
Have you thought about generalizations to other tensor networks?
So in this, what we thought about a little bit is about the non-translation invariant case, where you sort of like have a different, where you would also have a different group element at each edge. And it's a little, like the resulting fundamental theorem you would get is a little bit less natural, but in principle, you could also do this. And I think sort of a thought we had is that maybe, for instance, if you look at, say, Gaussian fermionic tensor networks, then there's also some natural symmetry group. And there you could also, in principle, apply the same machinery. So those are some of the things we thought about.
Thanks.
Steph?
Thanks for the great talk. You may have said this, so I may have missed it, but is there negative results regarding the complexity of your last question, improving algorithms for computing? Like, what's the complexity of computing this T-min?
Oh, yeah.
You said it's decidable now, right? It's not...
Right, yeah, so it's a great question, and there are actually some subtleties here that I did not really address. So yes, you can compute this T-min, but actually this problem of deciding whether two tensors give rise to the same thing on an arbitrary graph, it's clearly decidable because I just have to check a finite number of graphs, so it is decidable. But actually here, there is still this unitary the choice of freedom. So if I compute these two things for S and T, I still have to check unitary equivalence, and that's actually also non-trivial. We don't know how hard that is. So that's also there.
So Frank had a question.
Thanks for the nice talk. So in the case of PEPS, it is known that there's more general gauge transforms than the one you considered, namely in terms of matrix product operators. And then these lead to kind of new versions of fundamental theorems that are like not encompassed by your thing. So is this something you can deal with? Because it is known that very different PEPS representation can have the same, lead to the same state.
So we have not at all thought about these MPO symmetries. I mean, if something could be said about that, it would be very interesting. In some way, what we do is sort of course, much simpler than that. And indeed, So of course, our canonical form will not be able to distinguish certain tensors that give rise to the same lattice state. So because there's just this barrier to that. So I'm not sure if this answers your question.
Yeah, very nice talk.
Okay. Jens has a question.
Is it obvious, how to relate it to the previous question, to read off properties like the tensor being G-injective on the level of this minimal canonical form? So can you see, you have had this on the last slide, how is it related to topological order and other symmetries of the PEPS?
Yeah, so I think, I'm not sure if this answers your question, but one thing I can say, which is maybe interesting, is that in this definition, there's sort of this issue of whether you have to go to the closure or not in your optimization procedure. And for instance, when you look at injective, normal, or quantum double models with abelian groups, you see that you don't have to go to the closure, whereas there are also explicit examples with sort of, I think, non-abelian groups or just some slightly broader class where you do have to go to the closure. So that's some distinction that we see, for instance. But yeah.
Okay.